In this problem, we're going to be solving for three pipes arranged in series. And if you haven't already watched the video where I go through three pipes arranged in parallel, it's the same three pipes. We're just now going to look at them in series instead of parallel. And so in this case, we're going to be using a different set of relationships, right? So in contrast to the pipes in parallel system, we're going to be using a different set of relationships in order to relate the head loss and flow rates between these three pipes. So let's start with the easy one, the easy relationship here, which is just flow rate. So total flow rate Q through the system, right, whatever is coming in and leaving, coming in at point A and leaving at point B, um, actually has to be the same through pipe 1 and 2 and 3, just by mass conservation, assuming that this is an incompressible fluid. We're also generally going to be assuming, in this case, Newtonian and Moody charge holds. Um, so we can use the Moody chart to look up our friction factors. In this case, we're also going to ignore minor losses, just to get a sense of how to set up this type of problem in the first place. Um, okay, so we have Q, the total flow rate is equal to Q1 is equal to Q2 is equal to Q3. So the other piece that we need in order to get started on this problem is that the total head loss, so delta H total. In this case, because that change in head in this system is going to be due to differences in pressure and elevation, and therefore it's going to have to add as we move from the left to the right. So in this case, delta H total is going to be H1 plus H2 plus H3. So again, if you compare this to the case for pipes in parallel, you'll see that these two relationships are more or less inverted from one case to the other. But if that's new to you, then please go back and review the pipes in parallel example. Okay, so we need to get started here. So we're going to get started by computing this delta H total based on the data that we're given here. Right, so delta H total is going to be equal to the PA minus PB over rho G plus ZA minus ZB. If we work that out, so it's 150,000 pascals over 1,000 kilogram per meter cubed times 9.81 meter per second squared plus 5 meters, and that's going to work out to 20.3 meters as our total head loss across the system. And so our basic solution method here is going to be to construct a relationship which will let us quickly iterate to find our solution, because in this case we know L, D, and H. We're trying to find Q or V. So your textbook calls this a type 2 problem, and it generally involves some kind of an iteration when we have turbulent flow. And therefore, our solution method is going to be to find some kind of relationship that we can quickly iterate on that relates the velocities, the unknown velocities, the flow rates, back to the friction factors, and then we're going to be using the Moody chart to go through a few iterations. We'll see that in contrast to problems with a single pipe, things are going to be a little bit different here, but not terribly much. Okay, so for pipes in series, since we have the total head is a sum of these three heads, we can write out that this total delta H total, which is equal to 20.3 meters, this is going to be, right, ignoring our minor losses, this is going to be v1 squared over 2g times f1 L1 over d1 plus v2 squared over 2g times f2 L2 over d2 plus v3 squared over 2g times f3 L3 over d3. So on its own, this isn't really enough for us to get started. We have to also use the other relationship that Q1 is equal to Q2 is equal to Q3. So we can put all of this in terms of at least just a single velocity. What we're going to do here, we're going to follow your textbook and we're going to relate V2 and V3 back to that V1. So we know, so let's see, so let's start with Q1. That's going to be equal to pi over 4 times d1 squared times v1. We know that's equal to Q2, which is pi over 4 times d2 squared times v2. So therefore, we know that v2 is equal to d1 over d2 squared times v1. And similarly, v3 is equal to d1 over d3 squared times v1. And if we plug in our numbers for that, we're going to get that v2 is equal to 16 over 9 times v1, and v3 is equal to 4 times v1, just based on our known diameters of these pipes. So with that, we can now simplify our relationship. We're going to plug those into this delta H total relationship and start to get moving here. So we're going to have 20.3 meters is equal to, we're going to be pulling out a factor of v1 squared over 2g. That whole thing is going to be multiplied by, first of all, f1 times L1 over D1. L1 is 100 meters and D1 is 8 centimeters. So F1 times 100 over 0.08 plus F2 times, first of all, L2 over D2, so 150 over 0.06. But times, remember we have to convert between our V2 and our V1, right? So this is going to be relationship between V2 and V1. This is 16 over 9, and that's squared, right? So it's going to be F2 times 150 over 0.06 times 16 over 9 squared, plus F3 times L3 over D3. L3 is 80, D3 is 4 centimeters, so that's 80 over 0.04. And again, we have to convert between V3 and V1. That's going to be times 4 squared, because we're considering the ratio to get to V1 squared. So if we work that out, we can put this into a form that's just a little bit easier for us to iterate on. So we're going to have that, let's see, so 20.3 times 2 times 9.8 F1. So we're going to have 398. 398. That's going to be units of meters squared per second squared. Is equal to V1 squared. Remember, V1 is still unknown. Times F1 times 1250 plus 7900 times F2 plus 32,000 times F3. And so this form here, this is very similar to the way we've been iterating on type 2 problems when we have just a single pipe. But in this case, we have three friction factors, which are all potentially different, right? In this case, if we look up at our chart, each one of our pipes has a different epsilon over d, and so we do expect these friction factors to be a little bit different from one another. And they're all different diameters, they all have different velocities, so these things are going to be different from each other. And so when we're doing our iterations with the Moody chart, we're going to have to look up three different friction factors. But once we've done that, looked up, or to start with, just guessed those three different friction factors, we can then use this expression to directly compute for V. Once we've computed V, we can recompute all of the different Reynolds numbers. Remember, each pipe is going to have a different Reynolds number, and then start the iteration. So we're going to guess fully rough to start. So let's go and start with F1. So for fully rough, friction factor 1, epsilon over d of 0.003. So that's going to be right here between 0.02 and 0.04, something like that. If we trace that over, right, we're going to get a value of about 0.026. Okay, so we're going to initially guess F1 is 0.026. F2, so again, we have a different roughness here, is 0.002. If we look, that fully rough value, right, just to say right at that boundary there, is going to be, let's just double check that. So this is 0.29, 0.29, 0.28, 0.27, 0.26. Oh, sorry, that's that value is 0.025. F1. And our friction factor 2 at 0.002 is going to start just below that other line, so we're going to call that 0.0235. And our friction factor 3 for roughness ratio epsilon over d of 0.005, so that's right up here. So we're going to call that, tracing that over, 0.03. So with those values, if we plug that in, so now we're going to have V1 is equal to square root of 398 over 0.025 times 1250 plus 0.0235 times 7900 plus 0.03 times 32,000. If we plug that in, we have 398 divided by 0.025 times 50 plus 0.0235 times 7,900 plus 0.03 times 32,000. And we're going to get V1 is equal to 0.58 meters per second. If you're following along in the textbook, you may note the textbook actually uses an initial value of 0.026 instead of 0.025 for F1. But because this flow is so restricted by that pipe 3, you can see it really dominates here. We don't really actually have much impact even with that difference. Anyway, so now with that, V1 is equal to 0.58 meters per second. Now check Reynolds number to see if iteration required. And so we're going to get RE1 is equal to V1 D1 over nu. So that's, we already have V1 0.58 times D1 is 0.08 over 1 times 10 to the minus 6. That's 0.58 times 0.08 divided by 1e minus 6. So that's 46,400. So definitely turbulent, but if we look up here, a Reynolds number of 46,000 and a roughness of 0.02. So that's going to put us right squarely in this. So that's going to put us right squarely in this transitional range from fully smooth to fully rough, and so therefore we're going to need to iterate. Right, so it's turbulent, but not fully rough. For epsilon is equal to 0.003 epsilon over d. RE2 is going to be equal to V2 D2 over nu, and that's, we know that V2 is V1 times 16 over 9 times D2 over nu. So that's 0.58 times 16 over 9 times 0.06 over 1 times 10 to the minus 6. So that's going to be 0.58 times 16 divided by 9 times 0.06 divided by 1e minus 6. So that's going to be about 62,000. And if we check that for our roughness of 0.002, so now we're at 62,000, so we're right about here. And that is also in the same region, right? Same for pipe 2. And now let's compute RE3. It's going to be V1 times 4 times D1 D3 over nu. So that's 0.58. Plug in the units here, meters per second times 4 times 0.04 meters over 1 times 10 to the minus 6 meters squared per second. We can see that the units cancel out, and our Reynolds number is dimensionless as it needs to be. 0.58 times 4 times 0.04 4 divided by 1e minus 6. And we get 92,800, or about 93,000. And again, if we go up here and check, we're going to see that epsilon over d of 0.05, Reynolds number of just under 10 to the 5th. We are also in this transitional zone. So from here, all three pipes in transitional zone between fully smooth and fully rough. Therefore, iterate. But for an approximate answer, we're going to use our answer that we have so far, which is current V1 is equal to 0.58 meters per second. And we know that Q total is equal to Q1 is equal to Q2 is equal to Q3. So we can just use our Q1 to find our solution. So it's going to be pi over 4 times V1 times our D1 squared, which is 8 centimeters, 0.08 squared. So Q is going to be approximately equal to 3.14 divided by 4 times 0.58 times 0.08 squared, 0.003 meters cubed per second. And your book put this into units of meters cubed per hour. And so we get an answer of 10.5 meters cubed per hour. And your book notes that we can go through and iterate on this, and we get the final answer, final converged solution is 10.2 meters cubed per hour. But this 10.5 is certainly close enough. And on an exam, as long as you told me that you would iterate and why, right? It's important to know that you would iterate because all three pipes are in this transition zone between fully smooth and fully rough. Then this answer would definitely be sufficient. So I encourage you to go back and look at the example that I posted for the same three pipes, but run in parallel, or you would see sort of the reciprocal of these laws at play. And thanks for watching.